This is a lecture on sequences and series for Chapter 7, Math 107. The words sequences and series are very similar sounding. They also both start with S, and that leads to some confusion. A sequence is an ordered list. The series is the sum of the elements of that ordered list. So beginning with a sequence, the sequence is an ordered list, and this is the operative word here, a list. It can be a list of anything, any events, but of course we're going to talk about numbers here, although in future math classes it might not exactly be numbers, it might be functions, there might be all kind of things that you talk about. The whole idea is you have a list of things, and that list is ordered. If it's not ordered, it's called a set. Another S word, which leads to confusion there. So set has no order, it's just a list. It's a group of events, items, whatever. The sequence is the same as a set, except it has order. And by order, I mean that if this is an example of a sequence, then the 2 is first, the 4 is second, the 6 is third, etc. This would be a different sequence. The 3 dots means it goes on forever, but even if it didn't go on forever, even if it was just this right here, okay, I'll just put parentheses instead of the brackets, even if it was just those 5 numbers, if it was in a different order, it would be a different sequence. So sequence has an order to it. Because it has an order, you can think of it, there's this other definition which some people like, such as myself, and you don't have to worry about it too much, but you might want to think about it. It's really a function, and it maps the counting numbers, depending on whether you start with 0 or 1. But you start with some number, in this case I'm starting with 1, and you map that into whatever the elements of the sequence are. In notation for this idea, and you just have to know the notation. If the idea is not clear, then just learn the notation. You're going to denote the sequence by a list of variables, similar to what was done with the matrix, but they only have one dimension to them. So you call them A1, A2, A3, A4, meaning the first one, the second one, the third one, the fourth one, and then you assign the value. The first one is 2, the second one's 4, 6, 8, and that just goes on in this list. That's for this particular sequence. And that sort of ties the idea together that you have these particular numbers, but they have to be in this order. And the 1, 2, 3, 4 keeps them in that order. Now instead of just writing that sequence out, you can also write a formula. And the formula for a sequence is called a recursive definition. And the word re in the recursive means that you look at the previous terms to generate the next term. Or you look at the counter to generate the next term. In other words, it's a definition in which the list, the elements of the list can be defined. Now this recursive definition has to have 2 parts, and sometimes they're combined. In the 2 sequences we're going to study in a few minutes, they're combined. But here's the 2 parts. It has to specify the first term. You've got to specify where you start somehow, right? Then the second part of the formula, you have to find the nth term based on the previous terms. So, for example, if you have one sequence and it looks like this, say 3, 6, 9, etc. Okay, the first term is the 3. So you would have to say A1 equals 3 in your definition to know where to start. You could have something that looks similar to that, but maybe it starts at 6. Okay, so you'd have to specify for this sequence, this would be sequence number 2. Well, I don't even want to label them right now. A1 would have to be 6. So that specifies the first one. I'm sorry, the first term. It's a little trickier sometimes to figure this out. Oh, here's an example. Let's say the sequence is 25, 28, 32, 37, 43. Okay. So I want to write the recursive definition for this. So I have to specify where it starts. It starts at 25, so I say A1 equals 25. That gives me my starting point. Then I need to specify the next term. Oops. I'm going to write a formula now. AN is going to be the term I'm talking about, and it's going to be written in terms of whatever the previous term was in this case, so n minus 1. Let me do something simpler first. Let's do that. Fibonacci sequence. Here's the Fibonacci sequence. Well, I can start with 0. As you might have known from studying in some science classes, the Fibonacci sequence, it's a very interesting sequence. It's attributed to Leonardo da Pisa, who was called Fibonacci, and he went and studied at the Persian libraries, and they had the Persians had been over to India, and there they had met the Indian and the Chinese mathematicians, and they had learned many things and brought them back to those libraries, and he went there and studied that and found this particular information here about this particular sequence and how interesting it was, and he brought it back to Italy and to Western Europe, and after that people forgot where they originally got it from, and it just becomes attributed to him, but actually goes back to India and China. You will see this sequence, and ideally in an ideal many flowering plants, for example, for the cone on a pine cone, you start off, well, then you wouldn't start with a 0, but you could start off, you can see you'd have one of those little woody petals there. The next row around will have 1, the next one will 2, the next one 3, the next one 5, the next one 8, the next one 13. Same if you had the patience to start counting the seeds on a sunflower, you know, the flower of the sunflower seeds. It is almost, this sequence is almost followed by the distance between the planets. So it's a very interesting sequence in the sciences. Okay, so I want to write a recursive definition for this, so I'm going to say A1 equals 0 because that's a starting point. Now if I look at it, and this takes some cleverness, when you try to figure out the next term right here, you've got to kind of just look at the sequence and see what you can figure out. There's no set rule for it. But if you just sort of notice the pattern, this term is the sum of 1 plus 1. The 3 is the sum of 1 plus 2. The 5 is the sum of 2 plus 3. 8 is the sum of 3 and 5. So you see that the next term is the sum of the two previous terms. Now here's the notation for that. Here's the term I want to compute, an. And in this case, it's the sum of the previous one. So I'll put in an minus 1, and here's the one before. This might look a little bit obscure to you. Let's say that n was 5. So if I want to compute the fifth term, I'm looking at, and this says n minus 1. Well, n was 5, so 5 minus 1 is 4. And now I have to subtract 2 off the 5, and I get 3. So you see, this would make the fifth term be the sum of the fourth and the third terms, which is what we see up here in this sequence. I'll give you another example. Say you had the 100th term. Then this formula would tell you it would be the sum of 100 minus 1, which is 99, plus the 98th term. So you have two things going on here. You have, you're using these subscripts, these counters, to tell you which term you're trying to pick. You're doing some arithmetic on the counters as well. Here's n, whatever n is, that's when you want to compute. That equals a to the n minus 1. Well, if n is 5, n minus 1 is 4, plus a n minus 2, so n minus 2 is 3. Now we'll look at the other sequence up here that's typed. And here's the sequence we're talking about, so we specified the first one, and then here's the rule, which, let's just say this is the rule, we don't have to, we'll just kind of verify it. So it's the term I want to compute is equal to the previous term, plus whatever the counter value is plus 1. Okay, let's try that. Let's say a to the 5th would be a to the n minus 1, which is 4. Now the counter suddenly pops up here and becomes part of the calculation. And that's acceptable too. You won't have to do anything this hard. Okay, this is just to show you how it works. So a2, which would be your 28, you hope, equals a1 plus whatever the counter value is, which is 2 plus 1, so that's 3, so there I get my 28. Now I'm just going to mention this just as a passing. You can take the numbers 0 and 1, and from that you can generate all the numbers you need. Alright? And the way you do it is construct this arithmetic sequence once you have defined, of course, the operation of addition. Let's start with 0, okay? And then we have an equals an minus 1 plus 1. That means I start with 0, and I add 1 to get to the next number. I add 1 to get to the next number. I add 1 to get to the next number. There you've got all the whole numbers. Of course, you can use arithmetic inverse. Now that you have the numbers, you can generate the rest of them as well. Those are called Peano's axioms.